Hi everyone, my name's Tatiana and I'm iOS developer for over 10 years. During this time I had a lot of interviews and I also was interviewed many times, and today I tell you what the question about multithreading in iOS are popular in job interviews. Let's discuss iOS tool for working with multithreading. The most popular are Grand Central Dispatch or Dispatch Framework according nowadays Apple documentation, and Swift Concurrency. Despite the Dispatch framework is a really old library, we still use it actively, especially in large projects. And GCD multithreading model is based on use of dispatch queues. Thread management, including thread creation, is provided by queues instead of direct call thread command. The most commonly used tools are dispatch queue, dispatch work item, and dispatch group. Swift concurrency, it is not a synthetic sugar, and it is not some kind of wrapper over GCD. Swift concurrency is a modern paradigm of multithreading and different approach for working with threads, based on use of cooperative thread pool. A number of threads corresponding to the number of cores are created in the system at once, and then all tasks to be executed are distributed among these threads. Swift concurrency uses new primitives task and actor. Besides these tools, there are other ways to working with multithreading in iOS, such as a class thread and operation. But they are quite old and not often asked about in interviews, so I'll give you only general description of these classes. Use class thread to run your own thread of execution. Use direct threads creation with prudence, because threads are limited resources of the system, and Apple recommends using high-level tools for multithreading instead of using these tools. But there are some useful information commands: is main thread or current thread description. Class operation, all technology that allow to create cancelable and resumable operation and make dependencies between them. This class implementation is based on GCD, and modern approach for task management is to use a structured task tree in Swift Concurrency. And further, we will consider only Swift Concurrency and Dispatch Framework. Let's start with a trivial example with dispatch queue. Here we see asynchronous switching to the main queue from the main queue. The asynchronous block that print the 1 is added to the main queue after the sync code that print 2. The output will always be 2, 1. Let's modify it a bit by adding a serial queue. However, despite the similarity of the previous example, they are different. We execute print 1 and print 2 in two different serial queues, and the result of execution of this code is not defined. It may be either 1, 2 or 2, 1. Here, a stereotype is exploited. The async block often is executed after synchronous code, often but not always. Let's consider synchronous switching in a serial queue. The sync call will block work in current queue, waiting for switching to the specific queue and executing its block. If we try to switch synchronously from the same serial queue to the same one, we'll get a deadlock. This is true for main queue as well as for any other serial queue. For concurrent queues, there will be no problem in this case. And now, more interesting example. Dispatch queue concurrent perform is often used in interviews. Here's a cycle with thousands of concurrent iteration, and according Apple documentation, concurrent perform waits for all operation to be completed before returning. In this case, it means that at moment of printing, the value will be final. But what value we will get? Anyone who listened carefully to the previous example should answer correctly that the output result is undefined, and can be any from 1 to 1000. Additionally, we can say there is data race here. The concept of data race is easy to remember using this example. Please experiment and you see that the results are changing. But that's not all the problems with this code. We used the atomic type, but what if we will use an array? I would like to note that some developers associate atomicity with a value type. It is not the same thing. Multithreading access to a critical section without any protection may destroy your data. And what we need to do to save our data? I'll give you a simple example of critical section protection via serial queue. There is one of several popular methods. Class logger stores data in a private array log array, and for reading and writing is used a serial queue. Now we get rid of data arrays, and our array has 1000 records. Will this rows in order? No. This situation is called race condition. Difference between data race and race condition? It is not a very popular question on job interviews, but it is a quite confusing thing in multithreading. So, now is a good time to explain this. Data race occurs when one thread accesses data that is being changed by another thread. This error may lead to data destruction. Data race is a problem of a lack of critical section protection. Race condition is not a problem of critical section protection. Race condition is a logic error that cannot be solved by protecting a critical section. For example, if in previous example we need to get array with ordered elements, we need to take care about it beyond protecting the critical section. We considered several examples with serial queues. To create a concurrent queues, we just need to add the attribute concurrent. Use concurrent queues prudently, as they can generate a lot of threads and cause system overload. Also, Apple provides several out-of-box concurrent queues. I'll talk about it when we come to priorities. And now, take a look at the examples. We have serial queue and two blocks, print1 and print2 in both cases. In first example, we set up block priority such way that firstly is a low priority background and then come the higher priority utility. In second example, we don't have any specific priority for blocks, but firstly is asynchronous call and then synchronous. What we will get in the output? The output in both functions will be 1, 2. Tasks in a serial queue are executed sequentially, even if they have different priorities. This example demonstrates a particular case of priority inversion. The task with utility priority waits for a task with background priority to complete. The system will resolve this inversion by increasing the priority to the first task. The second task exploits the stereotype. The asynchronous call will follow synchronous one. Prioritization plays an important role in multithreading. The task order is defined by their priorities or quality of service classes. There are 4 main cores that are shown on the screen and also default cores. I'll tell a little later about the work of default cores. According to these priorities, iOS provides 5 out-of-the-box global concurrent queues. They exist in application and developers does not need to create them. We can use them as we can use serial queue main. The left example we've already considered. We've got 1, 2. And now right example with task in Swift Concurrency. There is definitely no priority inversion here. The probability of output 2 then 1 is very high, but we can't strictly guarantee this result because the task can be executed concurrently. In this case, the completion moment of each task is not defined. Also, tasks can be executed sequentially. Tasks inherit a parent context. So, if doSomething function is executed, for example, on a view controller, then both tasks will be performed on the main actor in order of priority. I promised to tell you about default cause, since many developers think that is one of the 4 queues with specific priority. This is absolutely wrong. This is queue in which tasks can have different priorities. Now, example. We create a queue with default cause in viewDidLoad function, which is launched on the main thread. And we add 3 tasks in this global queue. First 2 tasks will be enqueued with priority background and low. Low priority correspond to utility cause. We see explicitly specified priority in the tasks are saved. In the last task, the priority is not specified, so it will inherit it from the parent context, from context of function viewDidLoad, and priority will be high. Another example for comparison. What output should we expect from this function? In the second example, the output order is not guaranteed. I mentioned 3 frequently used tools in GCD. We considered dispatch queues. And now let's look at work item. The main feature of work item that it can be started, deferred, or can be cancelled. It allows us to implement various patterns, such as the bonds pattern, for example. Let's imagine you perform a search, and when you enter a new character, you create a new request and cancel the old one. We use perform method to start work item with request. To avoid a large number of requests, we can call the function with delay. In this case, we will use methods async after. Dispatch group allows us to make several requests simultaneously. Now, let's see how the same functionality may be implemented in Swift Concurrency. Creation of parallel tasks is done through binding async-let. The code looks clearer than the same with dispatch group, less chance of making mistake. However, there are still some non-obvious points. Let's compare 2 code fragments. In the lower code fragment, we have removed the intermediate variable. Will this code still work the same way? There is no async-let binding in the low code fragment, so no task for parallel execution will be created. The code will be executed serially. And now I will tell you about the question that I asked during interviews. What multithreading tools do you use in your applications to protect the critical section? What are the pros and cons of these ways? To answer this question, we need to remember what methods are. One way to restrict access through a serial queue has already been discussed today. You may tell about it. Next, situational question. After receiving answer of network requests and decoding data, function switches execution to the main thread and assign the result to a variable. What happens if we execute several queries simultaneously? What problems are possible here? We are again talking about the critical section, and it is safe to work with it on the main thread because the main queue is a serial. But this way is not completely safe, because you should ensure that all access to the critical section is from the main queue. If the shared data is not private, this method is not suitable. Explicit protection is needed. A serial queue or log in GCD or an actor in Swift Concurrency. Other potential problem is a race condition. Sometimes I hear from candidates that writing in the main thread is not optimal, and this method reduces performance. It depends on situation. If we write data through a serial queue, actor, or log, we must read it in the same way. But usually, we read data much more often than modify it. And here, we will lose more on reading than we will gain avoiding writing on the main thread. We are working with Swift Concurrency actively, and we asked about it at interviews. The first question, how to perform serial and concurrent tasks in Swift Concurrency, is easy to answer, and I gave code example with serial and concurrent task early in this presentation. This screenshot has already been shown. To obtain a concurrent execution, we need to use async-let binding. Without it, requests will be called sequentially. Making a network request with async-await, I assign data to some class variable. What potential problems are possible and how to avoid them? Since async-await requests are executed on the cooperative thread pool, you need to understand that the shared data is not protected from parallel changes in different threads. It is a potential error. To fix this situation, we can use an actor instead of class. What is an actor and what is it for? I talked about actors in the previous question and gave a code example. Actor is similar to an ordinary class, but the actor knows when its functions are running or property are being used, and does not allow its own synchronous code to be executed simultaneously. This guarantees the safety of the critical section. But asynchronous code may be executed concurrently. Sometimes actor is compared to NSLog because the actor solves the same multithreading problem, protecting the critical section. And the remaining question assume a deep understanding and experience with Swift concurrency. I leave this question for you, but I won't give an answer because a brief explanation may distort the meaning or will be not clear enough. And that's all. Thanks for being with me. I hope this presentation will be useful in your job interview as well as in your iOS developing. And good luck with your job interviews.